Testing, can you hear me? Alright, this video is public now. So I'm going to be studying calculus again. And then last time I studied surface integrals, learned about curls and divergence, and have some questions. There's some unclearness about the derivation of the surface integral formula, but I'll just keep that aside for now and then I will come back to it later. So Stokes' theorem. Stokes' theorem says we can calculate the flux of curl F across surface S by knowing information only about the value of F along the boundary of S. Conversely, we can calculate the line integral of vector field F along the boundary of surface S by translating to a double integral of the curl of F over S. Let S be an oriented smooth surface with a unit normal vector n. Furthermore, suppose the boundary of S is a simple closed curve C. The orientation of S induces the positive orientation of C if, as you walk in the positive direction around C, with your head pointing in the direction of N, the surface is always on your left. With this definition in place, we can state Stokes' theorem. Let S be a piecewise smooth oriented surface with a boundary that is a simple closed curve C with positive orientation. If F is a vector field with component functions that have continuous partial derivatives on an open region containing S, then integral of F dot dr is equal to double integral of curl F dot ds. Suppose surface S is a flat region in the xy plane with upward orientation, then the unit normal vector is k and the surface integral is curl F dot ds. This surface integral is actually the double integral curl F dot k dA. In this special case, Stokes' theorem gave integral of F dot dr is equal to the double integral of curl F dot k dA. However, this is the circulation form of Green's theorem. It shows us that Green's theorem is a special case of Stokes' theorem. Green's theorem can only handle surfaces in a plane, but Stokes' theorem can handle surfaces in a plane or in space. Complete proof of Stokes' theorem is beyond the scope of this book. We look at an intuitive explanation for the truth of the theorem and then see proof of the theorem in this special case that surface S is a portion of a graph of a function and S, the boundary of S and F are all fairly tame. First, we look at an informal proof of the theorem. This proof is not rigorous, but it is meant to give a general feeling of for why the theorem is true. Let S be a surface and let D be a small piece of the surface so that D does not share any points with the boundary of S. We choose D to be small enough so that it can approximately be oriented square E, so that it can be approximated by an oriented square E. Let D inherit its orientation from S and give E the same orientation. This square has four sides. Let denote them as EL, ER, EU, ED for left, right, up and down sides, respectively. On the square, we can use the flux form of Green's theorem. So these four is the double integral of curl F dot N is equal to curl F dot dl dot ds. Wait, going back to Green's theorem. So F dot dr qx minus py dA. This is the cross product with, yeah, this is the cross product, right? Sorry, this is the curl for two dimensions. To approximate the flux over the entire surface, we add the values of the flux on the small squares approximating small pieces of the surface. By Green's theorem, the flux across each approximating square is a line integral over its boundary. Let F be an approximating square with an orientation inherited from S and with the right side EL. Let FR denote the right side of F. Then EL is equal to minus FR. In other words, the right side of F is the same curve as the left side of E. Orientation in the opposite direction. Therefore, EL is minus FR. So integral over EL is equal to the integral over F minus FR. As we add up all the fluxes over all the squares approximating S, that the line integrals cancel each other out. The same goes for line integrals over the three sides of E. These three line integrals cancel out with the line integral of the lower side of the square above E, the line integral over the left side of the square to the right of E, and the line integral over the upper side of the square below E. After all this, the cancellation occurs over all the approximating squares. The only line integrals that survives are the line integrals over the sides approximating the boundary of S. Therefore, the sum of all the fluxes, which by Green's theorem is the sum of all line integrals around the boundary of approximating squares, can be approximated by the line integral over the boundary of S over the boundary of S. In the limit, as the areas of the approximating squares go to 0, the approximation gets arbitrarily close to the flux. F E H G I. Okay, so this gets cancelled out by this, right? This gets cancelled out by this. Is that what they're saying? Let's now look at a rigorous proof of the theorem in the special case that S is the graph of the function z is equal to f of xy, when xy vary over a bounded, simply connected region of finite area. Furthermore, assume that f has continuous second order partial derivatives. Let's see donate the boundary of S, and let's see not donate the boundary of D. Then D is a shadow of S in the plane and C naught is the shadow of C. Suppose that S is oriented upwards, the counterclockwise orientation of C is positive, as is the counterclockwise orientation of C naught. Let f x y z equal p q r be a vector field with component functions that have continuous partial derivatives. I don't understand how this is a shadow of this. D is a shadow projection of S in the plane and S naught is the projection of C. Shouldn't they be the same shape? We take the standard parameterization of S, the tangent vectors Tx, 1, 0, gx, and Ty, and therefore Tx, Ty is this. So double integral of curl f dot ds is equal to double integral d over this region. Gxy. Where the partial derivatives are all evaluated at xy, gxy, making the integrand depend on x and y only. Suppose x t y t from where t goes from a to b is a parameterization of c naught. Then a parameterization of c is x t y t and g x y. Where t goes from a to b. Armed with these parameterizations, the chain rule and Green's theorem, and keeping in mind that p, q, r are all functions of x and y, we can evaluate the line integral f dot dr. F dot dr. What is this? Clauret's, how do you pronounce Clauret's theorem? This is equal to this. Yeah, if you switch the x and y, they're the same. Therefore, 4 of the terms disappear from this double integrals and we are left with this. Is equals curl f dot ds. We have shown that Stokes' theorem is true in the case of a function with a domain that is simply connected, that is a simply connected region of finite area. You can quickly confirm this theorem for another important case when vector field f is conservative. If f is conservative, the curl of f is 0. So the integral of this is 0. Since the boundary of S is a closed curve. So this, okay, so this integral is also 0. Verify that Stokes' theorem is true for a vector field F and surface S where S is the paraboloid C is equal to 4 minus x square minus y square. Assume the surface is outward oriented and C is more than or equal to 0. So F is this surface area. So hold on. This chapter is quite difficult. I think the lack of, I don't know, I think I need to be really good at the previous topics because I read through them, but I'm not like good at them. Stokes' theorem, I'm doing this chapter for the first time. I think calculus, the book 1 and book 2, those were like revisions, but calculus 3, I'm doing this, all of calculus 3 is new to me. So vector field f x y z is y to z and then x square. Paraboloid z is equal to minus x square minus y square. Assume the surface is outward oriented and c is more than or equal to 0. So I think they want us to calculate this, and check if they're the same, right? So the curl for f, so f on the surface, f is 4 minus x square minus y square x square. 4 times 2 is 8. Uh, and then we want the derivative with respect to okay, let's do r u v is equal to, let's do take this as v. Zero, 1, this minus this. 4 times 2 is 8. This minus this. But the thing is, it multiplies with minus 1 because it's in the middle. This minus this. So it's just for you. And then what? Curl of f dot ds. And let me look at the surface integral topic again. Surface area. It's this part, right? This dot this. Curl f dot this. But hold on. Curl f. Um, y2z x square. I this times this minus this, right? So maybe just 2. This, which is 2x, minus this, which is 0. Then this becomes minus because it's unlimited. This minus this, which is just 1. If I do a curl of f in terms of r uv, then I have minus u minus 1 dot 2 times 8 is 16. 2 times 2 is 4. We have 8 u, right? 2v minus 1. Two minus 2 minus 2x minus 1. 2x 2y 1. How did they get this? G of x is minus 2x. G of y is minus 2y. Okay, it's still unclear to me how I'm supposed to do this. Stokes' theorem translates between the flux integral of surface S to a line integral around the boundary of S. Therefore, the theorem allows us to compute surface integrals or line integrals that would ordinarily be quite difficult by translating the line integral into a surface integral or vice versa. We now study some examples of each kind of translation. Calculate surface integral of this curl f dot ds, where S is the surface oriented outward in figure 6.84 and f is this. And then they did integral of f dot dr. Rt is sine t 0, 1 minus cos t. Curl of f is this. You have sine t 0, 1 wait, what? Shouldn't it be 1 minus cos t? How did they get Rt in the first place? F is c to xy x plus y. How did they figure this out? I have no clue. An amazing consequence of Stokes' theorem is that if S naught is any other smooth surface with boundary C, the same orientation as S, then curl of f dot ds is equal to the integral of f dot dr, which is equal to 0. Because Stokes' theorem says the surface integral depends on the line integral around the boundary only. Example 6.74, we calculated the surface integral simply by using information about the boundary of the surface. In general, let S1 and S2 be smooth surfaces with boundary C and the same orientation. By Stokes' theorem, curl integral of S1 curl f dot ds is equal to integration of f dot dr in curve C, which is equal to curl f dot ds S2. They're smooth surfaces with the same boundary. Therefore, if this is difficult to calculate, but this is easy to calculate, Stokes' theorem allows us to calculate the easiest surface integral. Example 6.74, we could have calculated curl f dot ds by calculating curl s naught curl f dot ds, where s naught is a disk enclosed by the boundary curve C. Equation 6.23 shows that flux integrals of curl vector fields are surface independent in the same way that line integrals of gradient fields are path independent. Recall that if F is two-dimensional conservative vector field defined on a simply connected domain, F is a potential function for F and C is a curve in the domain of F. Then integral of f dot dr depends only on the endpoints of C. Therefore, if C naught is any other curve with the same starting point and endpoint as C, then the integral of f dot dr and the integral of f dot dr in the different curves are equal. In other words, the value of the integral depends on the boundary of the path only. It does not really depend on the path itself. Analogously, suppose that S and S naught are surfaces with the same boundary and same orientation. Suppose that G is a three-dimensional vector field that can be written as a curl on another vector field F, so that F is like a potential field of G. In equation 6.23, we have G dot ds is equal to curl F dot ds. Is this? So G can be written as a curl of F. It can be written as this, which can be written back as G. Or if G can be represented as a curl of another vector field, then we can just use this, right? Therefore, the flux integral of G does not depend on the surface, only on the boundary of the surface. Flux integrals of vector fields that cannot be written as the curl of a vector field are surface independent in the same way that line integrals of vector fields that can be written as a gradient of a scalar function are path independent. Use Stokes' theorem to calculate surface integral uh, curl f dot ds where f is cxy and s is the surface as shown in the following figure. The boundary curve C is oriented clockwise when looking along a positive y-axis. So in order to do this, we just use FDR, right? F dot dr is one thing I want to line integrals. Is one thing I want to look at carefully. I don't know how long this is going to take. Oh, this is not line an example. Oh, this is an example. Calculate the line integral f dot dr where f is this and c is the boundary of the parallelogram with the vertices 0, 0, 1, 0, 1, 0, 2, 1, minus 2, and 2, 0, minus 1. So they're going to use curl of fxy dot dx cross product dy. Uh, dx cross dy. They did calculate this. Okay, this makes sense. If we derivate all this with respect to x, we are left with y, 2x, and it's 0. But what I don't understand is how they got this. 1, 0, negative 1, 0, 1, negative 1. Let's calculate the line integral using Stokes' theorem. Let S denote the surface of the parallelogram. Note that S is the portion of the graph of C is equal to 1, negative x, negative y for xy varying over the rectangular region with vertices 0, 0, 0, 1, 2, 0, 2, 1 in the xy plane. Therefore, a parameterization of S is xy1 minus x minus y. 0 to 2, 0 to 1. So x, y, z from 0 to 2, 0 to 1. That defines the parallelogram. Curl of f is, can I understand how they got the curve? But I don't understand how they got this. Dx, dy. Is it this over here? 1, 0, negative 1? Yeah, this makes sense. Okay, okay. If it's from this, yeah, then it makes sense. Right. In addition to translating between line integrals and flux integrals, Stokes' theorem can be used to justify the physical interpretation of curl that we have learned. Here we investigate the relationship between curl and circulation and we use Stokes' theorem to state Faraday's law, an important law in electricity and magnetism that relates the curl of an electric field to the rate of change of a magnetic field. Recall that if f is a closed curve and f is a vector field defined on C, then the circulation of f around C is the line integral f dot dr. If f represents the velocity field of a fluid in space, then the circulation measures the tendency of the fluid to move in the direction of C. Let F be a continuous vector field and let dr be a small disk around R with center P naught. If dr is small enough, then curl Fp is approximately equal to curl Fp naught for all points P in dr because curl is continuous. Let Cr be the boundary circle of dr by Stokes' theorem. We have this. The quantity curl F P naught dot N P naught is constant and therefore in this pi r square. Thus, we have f dot dr pi r square. Curl f p naught dot n p naught. And the approximation gets arbitrarily close as the radius shrinks to 0. Therefore, Stokes' theorem implies that curl f p naught dot n p naught is equal to limit as r goes to 0 plus. Okay, from the positive side. One over pi r square integration f dot dr. This equation relates the curl of a vector field to the circulation. Since the area of the disk is pi r square, this equation says we can view the curl as a circulation per unit area. Recall that if F is a velocity field of a fluid, then circulation F dot dr is equal to F dot ds is a measure of the tendency of the fluid to move around CR. The reason for this is that f dot t is a component of f in the direction of t. The closer the direction of f is to t, the larger the value of f dot t. Remember that if a and b are vectors and b is fixed, then the dot product a dot b is maximal when a points in the same direction as b. Therefore, if f is a velocity field of a fluid, and curl f dot n is a measure of how the fluid rotates about axis n, the effect of the curl is largest about the axis that points in the direction of n, because in this case curl f dot n is as large as possible. To see this effect in a more concrete fashion, imagine placing a tiny paddle wheel at point P0. The paddle will achieve its maximum speed when the axis of the wheel points in the direction of curl F. This justifies the interpretation of the curl we have learned. Curl is a measure of the rotation in the vector field about the axis that points in the direction of the normal vector n. Stokes' theorem justifies this interpretation. To visualize curl at a point, imagine placing a tiny paddle wheel at that point in the vector field. Notice that we have learned about Stokes' theorem. We can discuss applications in the area of electromagnetism. In particular, we examine how we can use Stokes' theorem to translate between two equivalent forms of Faraday's law. Before stating the two forms of Faraday's law, we need some background terminology. Let's say a closed curve that models a thin wire. In the context of electric fields, the wire may be moving over time. So we write CT to represent the wire. At a given time, curve CT may be different from the original curve C because of the movement of the wire. But we assume that CT is a closed curve for all times t. Let Dn be a surface with CT as its boundary. And orient CT so that dt has positive orientation. Suppose that CT is in a magnetic field BT that can also change over time. In other words, P has a form PQX, where P, Q, and R can vary continuously over time. Shouldn't if they can vary continuously over time, shouldn't T also be like, shouldn't they be a time input as well? We can produce current along the wire by changing field BT. This is consequent. This is a consequent of Ampere's law. Flux phi t, which is this, creates electric field that does work. The integral form of Faraday's law states that work is equal to this, which is equal to minus derivative of phi over dt. In other words, the work done by E is a line integral around the boundary, which is also equal to the rate of change of the flux with respect to time. Differential form of Faraday's law states that curl E is equal to derivative of partial derivative of B with respect to t. Using Stokes' theorem, we can show that the differential form of Faraday's law is a consequence of the integral form. By Stokes' theorem, we can convert the line integral in the integral form into surface integral. Since phi t is equal to bt dot ds, then as long as the integration of the surface does not vary with time, we will also have minus delta phi over delta t is equal to this minus delta b over delta t dot ds. Therefore, this dt minus partial derivative of p with respect to t dot ds equal to partial derivative is equal to integral of curl E dot ds. In general, this equation is not enough to conclude that curl E is equal to minus partial derivative of p with respect to t. Integral symbols do not simply cancel out, leaving equality of the integrand. To see why the integral symbol does not just cancel out in general, consider two single variables 0 to 1 x dx and 0 to 1 fx dx, where fx is equal to 1 from 0 to half, 0 from half to 1. Both of these integrals equals half. So from 0 to 1 x dx is equal to 0 to 1 fx dx. However, x is not equal to f of x. Analogously with our equation, we cannot simply conclude that curl E is equal to minus, what is this? Minus partial derivative of p, just because the integrals are equal. However, in our context equation, this equation is true for any region, however small. If f and g are three-dimensional vector fields such that integral of f dot ds is equal to integral of g dot ds for any surface S, then it is possible to show that f is equal to g by shrinking the area of S to 0 by taking a limit. Smaller the area of S, the closer the value of f dot ds to the value of f at a point inside S. Therefore, we can let area d shrink to 0 by taking a limit and obtain a differential form of Faraday's law. Curl E is equal to minus derivative of p dot over delta b over delta t. In the context of electric fields, the curl of the electric field can be interpreted as the negative of the rate of change of the corresponding magnetic field with respect to time. Calculate the curl of electric field E. The corresponding magnetic field is a constant field BT1 minus 4 and 2. 1 minus 4 and 2. We derivate this, right? With respect to t, but that's 0. So the curl is 0. Oh, okay. I mean, we did reach the end, but this is my first time doing calculus 3. So this chapter was really confusing for me. I need to get very good at all of the previous chapters because I'm sort of rushing through these chapters within these streams. I think after I'm done with, there's only one chapter remaining. After I'm done with this book, I will start a revision stream where I go like rigorously deep doing all the exercises. I think with calculus 2 and calculus 3, I will do like revision streams after I'm done, after I'm finished reading the calculus 3 book. Okay, I will end the stream here then. And yeah, I'll see you guys next time. Bye.